On behalf of the Department of Metallurgical and Materials Engineering, Energy, Rourkela, I welcome all participants in Microsoft Teams and YouTube for today's distinguished lecture on material science of sustainable metals by Professor Raabe, Managing Director of Max-Planck Institute for Eisenforschung, Germany. The Energy Rourkela's Diamond Jubilee Distinguished Lecture is jointly organized by the Department of Metallurgical and Materials Engineering, Energy Rourkela, and Indian Institute of Metals Rourkela Student Chapter. I'm extremely privileged to welcome Professor Raabe to today's distinguished lecture. Now I request Professor Anindya Basu, Head of the Department, Metallurgy and Materials Engineering, Energy Rourkela, for a customary introductions of Professor Raabe. Sir, please.
Good evening, everybody. On the behalf of the Institute and behalf of the department, I'd like to welcome Professor Raabe, who is currently the Director of Max-Planck Institute for Iron Research under Max-Planck Institute of Max-Planck Research Society. So our institute is organizing the series of talks for the Diamond Jubilee Diamond Jubilee celebration of the Institute, which was started its function in 1963. And today we are honored to have Professor Raabe with us. So it is a customary to tell a little bit about the speaker and who are from materials background. Everybody knows him very well for his distinguished achievement, but still this is my customary. So Professor Raabe studied music, metallurgy and metal physics at RWTH Aachen in Germany. He completed his doctorate in 1992 and habilitation on 1997 at RWTH Aachen and worked at Carnegie Mellon University, National High Magnetic Field Lab, and joined Max-Planck Society as a director in 1999. His interests are sustainable energy, microstructure, alloy design, computational material science, and atom probe tomography. He received the Leibniz Award and the ERC Advanced Grant, which is the highest European research grant. He was the selection board member of Alexander von Humboldt Foundation based scholarship program and member of Governors Board of Acta Metallurgica, member of Council of Science and Humanities of the German government. And there are a lot of achievements which we cannot discuss in the small time. His current Google Scholar Index is 135. From that, we can know his scholarly outcome. So with that, I will like to request Professor Raabe to deliver his talk on material science of sustainable metals. Please.
Yeah, thank you very much for the very kind introduction. And I now try just to share the content, and we first check whether everything is visible.
Yeah, it is visible.
Very good. Thank you very much. Yeah, then let's get started. As it was introduced, it's a big pleasure to be here today and share with you some ideas about the material science of sustainable metals. And as you will see, the first part is a bit more like a class, an introduction, while the second part goes a bit deeper into things. So I do this, of course, with a couple of very fine colleagues from the Institute and also from the ETH in Zurich. And I will highlight the contributions when we come to the respective topics. I think the assignment is quite clear to all of us. We have the, the interest in reducing the energy use and the CO2 emission through the use of materials. We do that indirectly through high-strength materials or through magnets, through, of course, better turbine blade materials or catalysts. So I think that is well known. But we also have an enormous CO2 and energy consumption, of course, particularly through the primary synthesis of materials like steels and aluminum or titanium. And that affects both the use of primary resources like ores, and that means when it comes to the CO2 emissions and energy consumption, we have been part of the problem, and I want to share with you some ideas how we could, our community could be part of the solution. And it's not a standalone challenge, but we have a couple of topics here that are interconnected. Not only the CO2 reduction that I mentioned, but also the use of green electrical energy sources for that are important, but also efficiency gained through artificial intelligence is an option. And of course, buffer energies like the use of hydrogen, and you will later see some examples. So that's a really complex system we are thrown in, and that catapults us from the early iron and bronze age into the age of sustainability, I feel. So let's walk through this in the context of a circular economy. So as I've mentioned, I think we all know there's substantial gain in these things through more efficient processes. And of course, we all work on materials for electrification and for sustainability enablers, like windmills or solar cell absorbers or thermoelectrics, better turbines, and so on. Another very important aspect that should not be forgotten is longevity and corrosion or hydrogen resistance, all materials and features that would serve higher sustainability, and particularly the design of materials for recycling. So I think many of our materials are still designed for one-time use, and there are many opportunities for advanced alloy design. But the point is, due to the growing markets, only about 2/3 can only be covered by using scraps. Because of the market growth, we still have, at least in the best of all worlds, 1/3 of the material coming from primary resources, from mining and reduction. And these processes are the biggest sources of CO2 emissions. And that means a really truly circular economy is not in reach, because the markets are growing much faster than the scrap availability grows. And this means that we have to include in our research, again, more crossover work between physical metallurgy and process metallurgy. So some acceleration factors. As we see, it's not just the population leverage, of course, but it's particularly the GDP. So the average increase of the wealth, which is really driving CO2 emissions and per capita use of metals, while the average industry improvement on carbon and energy is actually quite good. So an example, number 2, is the sustainability instruments. The point that we build a windmill or solar cell absorber that helps us providing sustainable green electricity does not per se make the instrument itself a sustainable machine, but you have enormous consumption of concrete, steel, aluminum, rare earths, and so on to build these machines. That means they are drivers of the global warming and material shortage themselves. That does not only apply for the wind turbines, for instance, but of course also for the solar cell market or for the rapidly growing electrification of the vehicle sector. A thing that is maybe sometimes underestimated is the huge relevance of construction. More than 50% of the steel that we globally produce, and that quantity is large, as you know, goes into construction. And these are gigantic quantities. And in the worst case scenario, another acceleration factor is rising water. So we must start and already do protect coastal lines against the rising tides. That means we have a 5-fold acceleration in the consumption, in the sheer growth of the markets, not just population GDP, but also providing green energy supply in itself as a driver, and then huge infrastructure, and in the worst case also coastal protection, where you need huge quantities of concrete and steel, of course. And that means that in this projection from the OECD, that we must build in that until 2060, the consumption of materials will double or even more than double. And that includes, of course, the use of metallic minerals like iron, copper, and aluminum oxides, for instance. When we look into sustainability, you have many facets, not just the energy and greenhouse gas emissions I referred to before, but also the question how toxic the effect is, or how it affects food, or the local water quality, or the labor quality. Another aspect that we shouldn't forget is the scarcity, the sheer availability of materials. I find that, phase diagram quite, telling here, where you see this distorted fields according to the availability. And we know we are not short of iron or aluminum ores or titanium ores. They are quite abundant, but many of these strategic elements, are actually very scarce. And we need those, particularly for communication science, for semiconductors and so on. And from this analysis, you learn that many of these really precious and critical or strategic materials for magnets and semiconductors are actually recycled to less than 1%. It means the recycling rate, and you later show a few more examples in this field of strategic elements, is very, very low. When we go back to metals, the punchline is that we have to address how to tame 2 billion tons of metals per year. And when you just look at the sheer numbers, that translates to about 8% of the global energy costs. The 2.5 billion tons of ores that we get out of the earth every year, and that builds up to 30% of the industrial greenhouse gas emission quantity. So that means on the positive side that when we have good scientific ideas, they can have a huge, huge effect. But we must quantify things. We too often see, kind of good or nice ideas that are not quantified. Let me give you an example of such life cycle assessment for the example of an aluminum can, which we all know. They have an average already a pretty high recycling rate, but the numbers are really staggering. They are, they are really big, as you see here. That's an old example from Mike Ashby's books, which is, by the way, a very nice introductory book for this type of topic. And you have to, address this in terms of 3 categories: the resource consumption, the emissions inventory. You must know what the emissions of your processes are and how this adds together to form a certain impact. And getting the data for these different categories is in part not trivial, and you can buy them. You have companies measuring that for you, but that's an important part of the calculation. And with these 3 different categories, as one example of life cycle calculation, you get to a total impact of not just your total product, but your process step. I find this here a very nice example I took from the literature about the same case, namely the aluminum can. And you see in the upper row, worst case scenario, where you have less than half of the aluminum that you use was only recycled content, and the rest was sweetened by liquid fresh aluminum from primary synthesis, but done by using fossil electrical power. When you go to the best case scenario, you have a very high recycled content, and the first factories are addressing now going towards 90-95% recycling rate, and you have a very high end of use recycling rate. You get down, to 10, 5, or even less percent of the primary carbon footprint of the worst case scenario. That also just is meant to show you there's no such thing as, a per se green or sustainable product, but you really must go through the entire manufacturing chain to realize, how sustainable or not sustainable a product is. And that has arrived on shop floor. So when you sell your steel or aluminum or other parts to the customers, we teach our students that you must provide data on the mechanical properties, on the functional properties, including corrosion, all these things that we teach our students. But now, or in the next years, you will have to address, what was the recycling rate? What was the greenhouse gas footprint? In other words, you must provide a life cycle assessment of your material, or at some point you won't sell it anymore. So this is really a completely new setting into which we are all thrown. Another point that I find quite interesting is the electronics industry that we often call the high-tech industry. When it comes to material science, in terms of sustainability, they are often really low-tech, and you later see an example. Or here you see unintended consequences like the windmill blades, which are in many places around the globe just used after scrapping for landfill. And that is not, the very purpose. And here you see the same thing for solar cell absorbers, where you see a lot of material being scrapped, which actually contains very precious and in part, of course, also poisonous elements. So which should enter the market back? And the coming wave for, say, LMO type of batteries is also very important because we have in a current car, for instance, electric car, up to 10 kilogram of cobalt. And cobalt, as you know, comes or is mined from Katanga in Central Africa and Congo. And you have implications regarding child labor, slave labor, all these things, or bad labor conditions that become now an essential part of this high-tech manufacturing chain. And that must be built in, must be considered. You know, we must tell the whole story, not just the part of the story that tells us there's a nice little green pony farm. There's not. And the same applies for deep sea mining. You know, there are this year more than 50 licenses for the Pacific Ocean have been issued to get these manganese knolls that most of us know from classes, because they are so rich in cobalt, nickel, and so on, because that is urgently needed for the current battery design. I told you to come back to the electrical waste. We have about 50 billion euros of electrical waste that are thrown away every year, and most of that ends somewhere as landfill, where again people under poor conditions must at least try to get the copper back from this waste. But this is no such thing as a sustainable chain. And when we look at mobile phone devices that we all hold so dear, we talk about 18 billion gadgets on the street by the year 2024. Well, the majority is simply not at all collected, and if they are collected, less than 20% is recycled. So you see a little bit that where my motivation comes from of emphasizing that the so-called electronics and electrical and also green industries are actually, when it comes to material science sustainability, they're actually very dirty. They are not green at all. And our job as metallurgists might be to, you know, find better means of making this more sustainable and viable. So we call that urban mining when it, for instance, comes to the post-consumer electronic and electrical waste. Just to show you the quantities, when you take the best gold mines in South Africa, where you get, you know, the material from more than a kilometer depth, you have 200 tons of ores to get 1 kilogram of gold out of it. You can get the same quantity of 1 kilogram gold from 3 to 4 tons of mobile phones, more specific from the computer chips in them. And currently, as you may know, there are different ways of doing it. You just crush it and smelt it and get essentially the copper out. The rest goes into filters or out in the air. And you know, the more advanced companies do that with electrolysis, of course, cathodic deposition of copper, that's a standard procedure. And then you have in the mud, of course, in the anodic mud, you have a lot of additional materials, like, for instance, the gold. That means you go through a staggered sequence of several electrolyses, but there's so much electrochemical research that can be done to do these things more efficiently, and there's a lot of money to earn. At the end of the day, you retrieve gold from this material. So I think there's a lot of research that has not even been started, which again has a high leverage. I already mentioned these high energy and CO2, consuming factors for aluminum and steel, but it's also worth noting that scrap production is another part of the coin, another side of the coin, because this is in part for many metals relatively high. The primary CO2 emissions for aluminum making is between 7 to 10 tons CO2 per ton aluminum, in part for some completely coal-fired manufacturing chains is even higher. While for iron, it is 2.3 tons of CO2 for classical blast furnace route. So, but the scaling in quantity, the gigantic market of 1.85 billion tons of steel is, of course, the big leverage. So we discuss sustainability throughout along two lines. One is the so-called direct sustainability. That is, you could also say direct CO2 avoidance, for instance. And the other one is the many indirect effects that we all, of course, have and work on, like magnets, high-strength materials, and so on, for fuel consumption, reduced fuel consumption, and so on. So here are some examples. So, of course, we have CO2 reduced production. I come back to this. We have massive electrification that's also in the steel industry ongoing, from electrolysis to electric arc furnaces and so on. Recycling is a massively growing market for all materials. And the question how we as material scientists can turn the recycling, the scrap and the dirt that comes with it into the material chain, how we can turn that into a real science. And of course, a few other direct measures. On the indirect sustainability, you all, I think, know what we mean, like weight reduction through high-strength materials. Of course, product longevity is still currently the biggest leverage. Damage tolerance and repairability of, through microstructure tuning, energy conversion efficiency through turbine blades, hydrogen-resistant materials, and of course, better conductors and energy harvesting materials like work on thermoelectrics and so on. The positive side, again, is that material science can influence most of the big sectors. So again, the metallurgist students are sitting, at the main pillar of influencing these required reductions in greenhouse gas emissions. And just an example for the indirect effect of steel design, if we were to build the Eiffel Tower today, we would only need 75% less steel than for the original design. Or this study of a body in white without the hang-on parts, just made out of commercially available high-strength grades of aluminum, steel, and magnesium, you arrive at a body in white weight of 270 kilogram. That is really super, super low. And we all know this translates in a linear function to reduced fuel and energy consumption when you operate the car. And particularly the luxury cars that we all like so much and so on, they are simply far too heavy just to cut costs. Many of these cars could easily be cut by a few hundred kilograms when investing a bit more into the high-strength materials for these cars. And some companies started making estimates when you have a vehicle with some high-end materials, aluminum, steel, that have been made with more sustainable footprint, then the costs are not so terribly high as we might think. So for a vehicle, for a car, you talk maybe 150 to 200 euros per ton of car when you make it sustainable. And for the washing machine, which anyway goes with a stainless steel through electric arc furnace, that difference is negligible. Here's an example where I just did such a calculation when you have a 1.7 ton, say, small SUV with standard materials as you would buy it now. When you use just current high-strength steels and high-strength aluminum alloys, you can reduce that by 400 to 500 kilogram easily. And just car companies always try to cut the costs on these otherwise very expensive cars on the materials side, and that of course translates to the weight reduction and lower fuel consumption. But the second point I want to make is that when you provide these materials from sustainable production, then you can achieve a product where you have maybe a third, gained by weight reduction for the operation of the vehicle, but also a third reduction of primary CO2 emissions and energy losses. So I think that is currently what we learn from industry and customers is kind of a double strategy that you must go. Better materials, but these better materials must be produced at lower carbon footprint. And of course, we all know one of the biggest players in this entire field is, of course, the field of corrosion. And part of that is, of course, research on hydrogen embrittlement resistance. That has been always a problem for all steels, high-strength steels, as you know, of course, but it's also a very big issue for high-strength aluminum alloys, meanwhile. Now, that is a little slide, a collection of some pictures to remind us that the scrap markets from which we want to get more and more material, up to 50–60% for some alloys, or for stainless even much more, you have a very complex kinetics. Some products, like here, the Brooklyn Bridge, one of the oldest steel buildings, where you maybe get the steel only back after 100 years or more, while like packaging materials can be back in the shelf after a couple of weeks. Now, the good side of all of that is, of course, that the materials market is gigantic. We talk more than 3,000 billion euros per day. And the question when we want to turn this market into a more circular and sustainable one, what are the real, basic research questions? So with that, I go a little bit more towards some more basic metallurgical research. So when we look into Scopus, we have more than 40,000 papers every year on climate change, on the fundamentals of climate change. When you look, on the primary CO2 avoidance, very little research is done. 150 papers on Scopus on sustainable metallurgy, or 300 papers on scrap recycling and so on. And that includes also the business side of things. So many papers are then addressing the business side, not the metallurgy of it. So there's huge headroom for basic research in metallurgy about direct CO2 avoidance. And we should just, as physical metallurgists, not be afraid of going a bit more in process metallurgy, because I think that's very rewarding, actually. So when we look first maybe into steel and follow this famous blog from Bill Gates, when he says, whenever I hear an idea of what we can do about to keep global warming in check, I always ask, what's your plan for steels? Let's try to give that man an answer. Here's again an overview from the World Data Platform, where you see that indeed iron steel is the biggest player. I mentioned that already. And here's just the redox reaction that really matters. Not just only that this slide shows this drastic growth of the markets. The steel market is really exploding in the next decades. But it's simply the fact that when you take the classical blast furnace route, or even some of the Midrex routes, then the use of carbon monoxide as a reductant is the main driver for this high CO2 production. And that explains these numbers that we have already mentioned before. And that makes, qualify steel alone for 30% about of the industrial greenhouse gas emissions. So these numbers are really gigantic. Now, when we look into the thermodynamics, we talk about 6 megajoule per kilogram of the free energy associated with the hematite oxide. There are many oxides, so it's for the hematite. And the actual efficiency that we currently have, averaged over the global industry, is 20 to 35%, which is already pretty good for the metallurgical sector. So many metals are far below 10% in the overall efficiency. Now let's take a step back into physics and chemistry. When we now say, okay, let's open up this question, what can we do better on the synthesis when it comes to this fundamental redox reaction? We have our feedstock, that is scrap, that are fine ores, very interesting because they are very inexpensive. We have lump ores, and of course, made from the fine ores, the quite expensive pellets. And now you can expose those to different reductant carriers, and that can be ions, protons, electrons directly, if you think of electrolysis, and molecular form. And again, you have different molecules or plasmas, how you can do that. We work on hydrogen, on ammonia, methane, methanol, but of course mixtures of these. And we even work with LOHCs. These are so-called liquid organic hydrogen carriers, because that's much more affordable rather than bringing liquid hydrogen across the ocean, which is of course a relatively stupid idea because of the energetic losses. And then you must see, where are these carrier molecules coming from? Do they come from water splitting, from electrolysis? Do they come from steam reforming, which again has a poor CO2 footprint? Or does the ammonia that we use come from Haber-Bosch, which is also not a clean process? Or maybe from pyrolysis, which is a relatively clean technique and produces solid carbon. And then you must again, for the life cycle assessment, blend in from which primary energy source these synthesis processes were fueled, both the metallurgical one, but also the one you need to get your reductant molecule or carrier. And we all know these overviews. Here you see the different variants of how to make steel. This is a classical blast furnace routes that I think we all know from our textbooks. Where you pump a lot of carbon in, end up close to the eutectic point, tap it, and get the carbon out in the LD converter by oxygen. And that gives this enormous, pumping of carbon in and getting the carbon again out. Now, the direct reduction based on these classical Midrex shaft furnaces, but also fluidized bed reactors, are interesting alternatives because they can be operated with hydrogen. And of course, electrolysis, but electrolysis is not our topic today. So just this classical blast furnace that we all know very well carries about 2 to 2.3 tons of CO2 per ton of steel. And again, there are different calculations pertaining to different companies, different plants, and so on. But give and take, we talk this amount of CO2 per ton of steel. And an alternative is obviously to use as a reductant hydrogen, because then you are producing water instead of CO2. And here we do these experiments with solid agglomerated fine ores that are agglomerated into the pellet form, about 1 centimeter size. And this is the industrial scenario that you know very well, and many such plants already stand in India, for instance, and where you use direct reduction, charge it with pellets, which in itself is a relatively costly and expensive process. And then you bring the iron sponge that you produce into the electric arc furnace, for instance, and do the ladle metallurgy and cast it and so on. And that has already a relatively low footprint if you would operate it with hydrogen. Currently, it's of course typically done with natural gas, for instance. And here's such a kinetics when I do that on a commercial pellet at 700 degrees centigrade with just pure hydrogen at 700, as I said. And then you go through that sequence, you can see the reduction rate here, the derivative, and go from the hematite, the original hematite ore, which is trigonal in the oxygen lattice. There you go to the cubic magnetite, further to the cubic wüstite, where it gets very slow, and further, of course, into alpha iron at 700. Now here you can see a very nice environmental movie, taken an environmental electron microscope by my colleague Professor Willinger at the ETH in Zurich, in Switzerland, where you see how the iron is growing on top of that oxide. Here's another movie with slightly higher resolution, where you see that the rough surface is the oxide, but the iron that forms of course on top where the reaction is taking place, and the mass transport is really fast. When you cast this into a schematic picture like shown here, you can see that the real bottleneck is that you must bring the oxygen ions through that firstly formed iron layer, which is here plotted pretty dense, so that on the next nearest surface the water as a reaction product can form. So you have these kinetic and thermodynamic settings that show that once an iron layer which is dense has formed, this process is indeed a bottleneck process, gets very slow. Now let's look into a real pellet. Here you have a hematite pellet, a commercial one, as I said. You run it in a secondary electron mode or look at the phase contrast with EBSD. Then you can nicely see this hierarchical structure. We have in the inside a polycrystalline substance with many grain boundaries and a lot of porosity around it that comes, of course, from the sintering. And this porosity is very important for reaction kinetics. Why? Here you see on this picture, after 1 minute at 700 degrees centigrade, you see the light blue is the hematite with the relatively big grains, and the orange ones, which is much finer, is actually the freshly formed magnetite. And as you see, they are not so terribly coherent. They have some plane match planes, but others do not match. So you have a relatively classical nucleation and growth type of problem, Raabe type of problem. When you magnify and look a little bit after 10 minutes into the microstructure, you see that where already much of the iron has formed. You see, however, when we go into these 4 different snapshots, that yes, you have a couple of ferritic regions which are surrounding part of the wüstite, and the last stage oxide is the wüstite, the FeO. But you see it's not entirely wrapped. You see there are areas which I highlight here that indeed have a delamination or crack and so, which is very important to understand because the high temperature mechanics play a very big role here. You also see here, when you get closer to some of these interfaces, that you build up, as you can see in the channeling contrast, very high populations, for instance, of dislocations. And so there's an interplay of that porosity, as you see here, the stresses. The porosity comes from the oxygen loss. So we show that here on this slide for a wüstite single crystal. And close to the surface, the porosity gets very fine and the oxygen in part can directly diffuse out of the surface when the reaction starts. While in the center, the porosity is leading, and the phase transformation volume change is leading to massive stresses and to diffusional pore build up. Now the porosity during that reduction step in a Midrex type hydrogen-based process, as you see here, can at the end of the process occupy between 40 and 50% of the entire pellet volume, while the inherent porosity was maybe about between 25 and 30%. So you have a massive increase of the porosity. here's such a pellet, and we try to do some theory and bottleneck theory and full field calculation on this. Again, we do the same analysis. We map the microstructure, the phases, the grain boundary, and so on, as you see here in this slide sequence. And then we use this information as a starting point for a phase field calculation. So what we do here is that we do a full field treatment where we use the phase transformation, of course, through the Ellen-Kahn theory, which is a non-conserved structural phase field. And of course, the rest is the classical Kahn-Hilliard theory where you solve the diffusional problem. And with that, we try to simulate, as you see here, the progress in the growth of the iron when you expose that piece of wüstite material to hydrogen. And you see in these areas, you really have the first contact. That means the first reduction always takes place where the hydrogen gets quickest to the oxide and the oxygen gets out. But you also see that on the inside, indeed, when a remaining wüstite particle is entirely cladded or surrounded by an iron layer which is dense enough, then the reaction at the end, as you saw on the kinetic curve, gets really slow. And that's what we want to understand. How should such pellets look like? How big should they be? What is the fracture mechanics of a pellet that you want for a reactor, and so on. And we do the same thing here also together with colleagues at ETH, with Malte Arik Beer in his PhD, where we study two-dimensional wüstite films, expose them in the environmental electron microscope to hydrogen, and see how certain iron nuclei are forming, what their wolf shapes are, where you have plane match, and so on. So, and then we go into high resolution. There's another example here where we study this by high-angle annular dark field imaging. And our special interest was here addressing the question on the percolation and topology of these pores that you see, particularly those that form and those that are inherited and from the sintering. And we want to understand what their role is for the kinetics and for the capturing of the water of the reaction product, because it's one of the biggest problems is how to bring the water out of the pellet and of the shaft furnace. So here we studied 3 different types of pores depending on their vicinity to the next nearest surface in this high angular dark field contrast. And we find, interestingly, that the pores that are more remote from the surface have to store the water that is being formed. And that is what you see here. And that leads, with a very high upcoming water pressure, which we again calculate, leads to a reoxidation of this inner rim of this pore. So that makes the reduction also sluggish. And then, of course, here you see in the atom probe analysis, you have massive influence of the type of mineral that you use, because many have now, of course, gangue elements. They have chemical tramp elements that in part form very, very stable oxides that you simply don't reduce. And that is something we only started to study because this is a totally different game. In classical steelmaking, you inherit your impurities from the coke, from the blast furnace, while here you mainly inherit all your impurities that matter from the oxide. So that might also be or lead to a situation where new, companies enter the market with different type of oxides. And we also work now with scientists in academia from this mining sector to better understand what kind of fine ores and what kind of bulk ores or pellets, what kind of chemical impurities play what kind of role in the overall reduction scenarios, kinetics, and of course cleanliness of the final product. All these things are entirely unknown, but so many things are in motion in the next decades of how steel industry will change that there are, again, many, many research opportunities to do such work. Now, another project we work on a lot is if you just for a moment forget the entire steel plant, just forget also the direct reductions, the classical Midrex, because you must go here through the electric arc furnace with whatever product you come up with. It's an iron sponge and you must melt it. And when you just forget all of that and just do all the melting and charging and tuning in one furnace, namely in the electric arc furnace. So that is a scenario that has been tried out by only a few groups when you operate a more or less conventional arc furnace, but you equip it with a small reduction atmosphere. And then you can arrive, depending on the quality of the electrodes, of course, and of additional fuels that you might use or so, with a very low carbon footprint. So I'm thinking of an aggregate like here that you can operate with sustainable electrical power, of course. It's after all, it's an electric arc furnace, so you directly use electric power. And that is really, really interesting in my view, because you don't need the buffer, so much buffer energy like for the direct reduction techniques. And then you charge your ores, your scrap, you can mix everything and melt it. You must not forget the melting point of hematite is only slightly higher than that of the iron. And that means you really can co-melt scrap and hematite, and by that also reduce it. And of course, we all know that these electric arc furnaces are a global industry standard. So that's a growing market, and you know, in all the steel producing countries, this is a total standard technique for scrap melting, particularly for stainless steels. But it can of course be used for any scrap material. And here we have such an experiment in one of our plasma furnaces that is now flooded with a mixture of argon and hydrogen, where we play, of course, with different partial pressures of hydrogen. And we are currently also working to understand details of the plasma a bit better. But you can here nicely see that you also have, depending on the gas and on the plasma state, you have different type of interaction between your arc and the type of oxide you melt. But at the end of the day, you arrive, as shown in this overview diagram, you arrive with this simple experiment with, as I said, in this case, only 10% hydrogen at a very efficient reduction method. Here you see the pictures of an interrupted process, after which we flooded the chamber again with the same gas mixture and so on and went on. You see a sequence, up to 10, 15, 30 minutes. And already more or less after 15 minutes, probably after 30 minutes, 20 minutes, you have pure iron in your hand. So with only 10% plasma content of hydrogen. So that's very, very efficient. This is just a nice little, appetizer picture where you see an iron nucleus in the solidified quenched iron oxide that surrounds it. That was just one of these intermediate 2-minute tests that we stopped, took out the material to, of course, better understand now the nucleation and the growth processes in the liquid, of course. Here's from the quenched 2 atom probe, where we see, again, we study, of course, the relevance of the gank elements, like here silicon, which sure partitions and plays an important role for the growth rate in the liquid. So I think this plasma machinery is a really interesting alternative. Now, in aluminum, when we switch gears towards the end of this talk, it's entirely different. In aluminum, we have this enormous energy demand due to the high free energy of the oxide to make primary aluminum, very, very expensive, as we all know. But the secondary aluminum making from scrap is very affordable and only needs about 5% of that energy demand because the melting point of aluminum is so small. And that is, of course, entangled with the corresponding development of the scrap market and sorting technologies. But the trend is very clear. When you look, the primary aluminum use is shrinking, while the recycled one is growing. We talk towards 50%. And that means we must much better understand what does it mean for our high-end aluminum alloys. And the second graph that I find important to consider is that the contribution from the post-consumer scrap, so in other words, low-quality scrap, mixed scrap that we produce, is drastically increasing. That means we do not just only have to consider how to build that scrap into our alloy design, but we must understand how to use very low quality scrap. And that is a real assignment, I think, for the aluminum alloys of the future. Maybe not in a plane, but maybe in your mobile phone or in your laptop or in your car, where you do not need the same quality sometimes, like in a plane. And another aspect is, of course, in any case, when you recall the life cycle statements I made before, to consider where the original power comes from, that not all primary aluminum is bad. You just must do a life cycle analysis to say, where does it come from? Now, aluminum is, from the physics side, of course, entirely different from steels. It has, as we all know, very low solubility, and hence any scrap, related tramp element can become an enemy. So we have these classes, as you all know, of silicon containing cast alloy blocks, where much will re-enter the market when the electric auto market is growing. Then you have the copper-containing high-strength grades, and particularly the iron-containing mixed scrap, which you get from cars and architecture and so back, and particularly from post-consumer scrap. Here you have an example, a little atom probe project I did last year with a Humboldt fellow, where we looked just into packaging aluminum, which was meant to be, of course, a relatively clean material, as you all know. And here you can see, just of course in terms of the size, strongly exaggerated, but you can see that you have an enormous number of elements in the alloy. And that is just highlighting the challenge that for the future design of aluminum alloys, we must, consider these many tramp elements that will increase to accumulate. And that means we are not so much talking just about the centers of phase diagrams, but we are talking about the corners of phase diagrams, yet with many, many dimensions, with many chemical components. That means we must maybe be capable of understanding how is the metastable phase evolution in aluminum alloys when we have 15 elements present. And that is not at all trivial, neither for kinetics, heat treatment, or metastable states. That means we have this overall trends that, we have maybe nowadays a too large variety of materials, with in part containing a third of the periodic system, like a product like a windmill or mobile phone. And when we only look into metallurgy, into our field, we have, of course, an increasing number of elements with massive compositional blends. And what we should not forget on the other side is that microstructure and properties are not conserved quantities like mass and energy. That means they can really be massively rejuvenated and tuned. And that is actually, of course, as we all know, at the core what our research is about, namely understanding the microstructures of the things that we make. And I think that brings many interesting research opportunities to bring these two things together. So you see here the main alloy trends plotted for aluminum alloys again, tensile strengths plotted as a function of the main alloy groups with the main alloying elements highlighted. And of course, we have to appreciate and accept that, yes, there is a strong influence by the composition here of a factor of 5 about, which is pretty high. But when you look only at the scatter bar for the high strength grades here, like 7,755, then you have a very huge bar that for the same composition obviously allows you to change these properties, these mechanical properties, not through chemistry, but through microstructure. And I think bringing these two things together, the chemical composition variation and the microstructure, is one of the big research assignments for the future. So I tried to order some of these things into TRL, technology readiness, which is always important because at some point we want to serve customers and products. And on the other side, what is the expected impact of some of these things? So real calculated life cycle impact of these measures. And then the biggest one in the left upper corner is, of course, corrosion and longevity, research on fatigue, stress corrosion cracking, things like that. Then we have a lot of synthesis related topics where, again, one should not be afraid. If you are not a process metallurgist, you should not be afraid of these things. There's so much overlap between physical metallurgy and process metallurgy that's really, I think, an area that I highlighted here a bit in yellow background color, which offers ample opportunities for quite fundamental research. Also in electrolysis, there's also for steel so much research to done on the electrodes, on the elementary reactions, on the plasma reduction. Everything that deals with ammonia and H2 as reductant has much to offer here. And so at the end, I just wanted to summarize that beyond the details I shared with you, I think we must always remain aware that the big numbers, are much, much bigger than the small numbers. And sometimes I feel there's too much discussion about sustainability in terms of really second order effects. But I think our field, metallurgy and material science, is an absolute, first order effect type of thing. When you have good research ideas to make just a little bit of progress in the CO2 or energy demand of iron making or aluminum making, you directly affect 2 billion tons of metals. So the leverage could not be bigger. And that I find is a fantastic motivation for basic and applied research. And the same applies for all these, electronic chip gadgets, laptops, mobile phones, mobile communication things. The same applies there, just that the focus is a different one. The total quantity is of course not so big, but we talk about integration of, a few atomic layers, where you have to answer the question, how do you get the gold, the silver, the silicon, the arsenic, and so on, and the copper back? So I think with that, I should stop here. And again, thank you very much for having me today.
Thank you, sir, very much for your delightful talk and such in-depth discussions on how to produce iron and steel environmentally friendly, and how we can progress to develop sustainable materials. Now I think that the session is open for discussion. The students, participants from NIT, outside NIT, can ask questions to sir. Before starting off the students' questions or faculty's questions, I'd like to ask two important questions that rises in my mind. Is that that aluminium has we call this as a green metal. We have a very good recyclability if you compare with steel. Now, if you try to get an understanding that, for an example, a gas cylinder normally that is being made of iron-based material. Still, we know that aluminium has a huge potential to produce a very good fuel economy as far as the gas cylinder is concerned. But still, the market shows that we are still far away from using aluminium as a gas cylinder specifically. I'm just taking one example. So how it is prospectful to replace steel, which is an established metal as far as this kind of usage. So can you put some light on that?
Yeah, I think that is all, to my view, more market-driven, not really so science-driven. I mean, this competition between steels and aluminum alloys is a very classical competition. It is not new, and it is not really so strongly connected to sustainability at all, because as I tried to show with some examples, short examples of the life cycle calculation, is that it depends very much on how a certain product is made, and neither aluminum or steel are per se, bad or good or whatever, but it must be simply documented. That's what I showed with this Tesla building part for the Model Y car. So whatever you sell, whether it's aluminum or magnesium or steel, to a certain product in the future, you will enter certain markets only if some of these sustainability measures are taken into account and are made transparent through life cycle analysis. And that then produces this leverage on how these materials are made. And aluminum is indeed very, very attractive. And the projected market growth of aluminum is extremely high because, again, not just the low melting point of aluminum, but also simply the growing scrap market. So the markets of the scrap are really important, but I had, of course, not time to go into this. But the availability of aluminum to be molten, that will drastically increase, and that makes aluminum very, very attractive. And depends on the magnitude of your product, but of course nowadays this is a big industry to provide better scrap sorting, because by that you vary the price of the aluminum by a factor of 10 easily. And you can get a feeling when you go to big web pages like Alibaba or so, when you want to buy scrap or so, you can really nicely screen and skim through the many prices depending on the purity of the scrap and how it is sorted and collected and so on. So yeah, I think that depends very much on these different market drivers. My experience is just that whatever the details of these markets are, metallurgists like we must have answers how you develop type of quality alloys, but maybe coming from less pure sources with higher impurity content. And aluminum is here a really difficult little guy because it does not like to bring things into solution. That means whatever dirt you put in aluminum, it ends up as a type of precipitate, decoration, Gibbsian isotherm type of segregation and so on. And I think that is a very interesting research topic.
Thank you, sir, very much. My last question is, that there is a severe usage of pulverized coal in iron making industries, pulverized coal, and to reduce the load on the coke oven batteries. So, sir, because coke oven has a tremendous influence on the carbon dioxide emission. So, what is the prospect of this usage of this pulverized coal? Is it replaceable by certain other facts that we can use certain other renewable energy sources, specifically with iron making, to make a competitive adjustment with pulverized coal or certain things which doesn't reduces so much of greenhouse gas emission?
Yeah, I think most of the intermediate routes or alternative into which many big companies, also Indian companies, are of course investing is a classical Midrex operation, so classical direct reduction, which is a quasi-industry standard already globally since many decades. And there they use natural gas, of course. And natural gas already has a better CO2 emission footprint than the classical blast furnace route. It has other problems, of course, associated with it. But then the trend will be, I think, to buy more mixed reduction gases that are not just pure natural gas, but you try to buy everything that you find on the market, including carbon monoxide and of course hydrogen containing gases. And by that you will not be entirely cost competitive compared to carbon carriers. But this market pressure from the customer will increase. That at some point, for some products that you cannot compete with pure carbon carriers like coal, but maybe if you get into high price sectors like the car industry or whatever, or mobile phones on aluminum, so then I think you will have to offer solutions that have this lower carbon footprint. So in a transition technology, I see more the Midrex operation as the next competitor on the market. But again, I'm more into these science problems. This is just my view of the global market development.
Yeah, thank you, sir. Thank you very much. Any other participants, faculty or students? The session is open for discussion. So anybody else wants to ask question to sir? I think there is no questions. Once again, I will thank a lot to sir for your precious time is given to us and enlightening with us with your detailed presentations that can lead to think alternatively how we can do to produce environmental friendly production units. So thanks you once again, and I also like to thank the faculty members, student members of IIM Rourkela student chapters. And once again, I would like to thank you, sir, for your precious time that you have given to us for enlightening us. Thank you, sir.
Yeah, thank you very much. Bye-bye.
Thank you, sir. Thank you.